So some preliminaries first. The first thing is that the age of nuopsy has begun. So up until, well, when we first created these tools and got it all set up, we were kind of in the MCT era, and which is basically based off of, CSM 2.2 release, and everything, all the tags at that release level and neighboring release tags, tags, have been very stable. So the scripts and the programs have been stable for those, and for all the tags kind of associated in that era. But as of the newest tag, CSM 2.3 Alpha 08A, we're fully switched over to the nuopsy coupler. And so everything that's going to be presented today is based on this version. So this adds a level of complexity that we haven't had to deal with before now with these tools, in that we need to be able to accommodate tags that are not necessarily compatible. So for older CSM tags, the tools, the users will have to go through, instead of just cloning the tools from the Community Mesh Generation Toolkit, they will have to, once they're in that directory, then check out the VRM tools MCT V10 tag. So that tag, I kind of put that off so that it's like an enshrined version that will work for all of the tags in the MCT era. But moving forward, if you check it out, you're going to have either the current tag or a newer tag in order for everything to work right. And if you do that, if you are in an older one, then in the docs directory, there's a AMWG February 21 demo files directory. It has the PowerPoint and all of the kind of the demo and the instructions for using the MCT version. So you refer to that rather than what we're going to talk about today necessarily. Okay, so one of the main focuses we're going to talk about today are going to be the new features that have been added. And those are the first one is there's a Gen Ref Map NCL program in the VRM editor directory. And what that does is it gives us the ability to change the resolution of the base reference map that we're going to use in the editor. So in the editor, we have a default map, a reference map with a default resolution that we edit, and then that is what we use to generate the mesh. And there are instances where that resolution is not sufficient. And what happens is you can't kind of get the fine details in making your region. It was always a problem in that people that had to have small refinement regions, it was too coarse, particularly once you got away from the equator to make those regions. So the Gen Ref Map, what it does is it creates a blank reference map with all zeros in it, but at a different resolution. And then we will read in those that new reference map, and the program will adapt and change its resolution internally, and then you can edit at a finer detail. The trade-off there is that you get a little bit less. You're a little bit less responsive on your actions and your mouse movements in the program. But that depends on how fast. If you're going over the internet or if you're just using a local machine, it's maybe not that big of a deal. The second new feature is that there are some new fill options for the rectangle and polygon editors that give the ability to do better, better adjustments and refinements to your maps. So you can use it to tailor your map and get rid of little blemishes in the grid that's generated. And that was not something that we were able to do before. And then the third thing is there's a manual editing option that was added in there. So you can save the output of the refinement on the grid file, and then use the standalone program Create VRM Grid to generate an edited map. So you save the file, you edit it, and then you run the command line program, and you're able to maybe have a little bit more control over the details of how your map ends up looking. And Adam we'll go through that, and Adam has an example he'll show us later on. So the first thing we're going to go over is the outline of using and creating the VR grids. Then we'll go through the process of creating the grids with the VRM editor and Squadron. I'll talk about creating all the input files that you need for your repository, and then establishing your defaults for that grid. And then in the end, we're going to talk a little bit about the maintenance that you're going to have to expect to deal with in the future as the model continues to evolve. So the usage scenario for these for variable resolution grids is you have your own repository that contains your grid that you create that you want to do your research on, and then you have all the files that are associated with that grid, and then that local repository is a supplement to the supported data archive at on Glade, and so the CSM will pick up the files from each of those locations as it's needed. And so you have a local repository that you maintain and you can share with members of your research group, and that way everyone's not having to redo the same thing of generating their own grid. And the idea, and it's worked so far, is that that one repository will not need that much maintenance. So as you change from tag to tag, as long as they're compatible, you won't have to go through and recreate all the files. You can just create a new case for the new tag and just use your grid as you did before. So there are 5 steps for creating the grid. First, you're going to get the source and all the build the executables. Then you have to go through a process of editing and creating a new grid, create your repository, and there's one thing I didn't add. So the mapping of domain, that's no, I guess I can't do it that way. Mapping of domain files are no longer relevant, and so I didn't edit that out in this version, so ignore that, but you'll have all the other initial data files in your repository that we'll create. Then there's an installation script that basically sets up the grid and the user nameless defaults for CAM and CLM for your files. And then you go through a process of iteratively adjusting nameless values to get a stable run for 5 days. And then from there, you have a working foundation, and then you can, if you need to do there's additional steps. If you need to do more scientific oriented work, if you have to create nudging data or chemistry emission files, or if you need to spin up a land file or an atmosphere file for your defaults. So if you look in the VRM tools directory, once you download the repository or the GitHub repository, you'll see a number of directories. The first 3, Squadron, VRM Editor, and VRM Control Volumes, those are the directories that contain the everything that you do in the first step for creating your new grid. Then there's a series of gen_ directories that are used to create your mapping domain and input data sets. And of course, the gen mapping and gen domain are now obsolete. They'll still be in there for kind of reference, and then to help out people that are going to have to have the difficult situation of having to be able to have a repository that supports both MCT and WAPC both. But those are essentially useless at this point, and they will go away in future versions. And then there's an installation script that you run once everything's created, and it sets up all the configuration files so that you can pick them up with a create new case command. There's a VRM diagnostics that has utilities and things for looking at grids and such as that. There's a docs directory and a README and such as that. So in the documents directory, there's the original PDF documentation for the editor, which you can reference for I guess historical purposes. There's a CAM T-steps PDF that it gives you a guide for establishing the default time step, nameless values for your new grid. I added a file revisions and known issues. This is where I will put things like these new features are kind of mentioned in there, and then there's like a list of known issues that exist with the editor and the whole process. Then there's 2 directories. There's the AMWG February 21 demo files. That's the older PowerPoints and related files for the MCT tags. Then there's a AMWG February 22 demo files. which will have the files for this PowerPoint and related files. That is currently not up there, but as soon as I'm done here, I will update the GitHub repository, and then that information will be available for future reference in that subdirectory of the tools. One other note is there is, if you look in there, you'll find a pre-built Mac executable for the ARM editor. That is an older version of the editor, and I'm not going to update and maintain that. It's just it's too much of a headache for me to do that. So for Mac users, you'll have to figure out how to compile the program with some help, or if you know how to do it, or else get a Mac guy to help you do it. I can't do it. So so in the demos directory, there's going to be a notes file, which is a text file, and that has the step-by-step commands that are used that I went through with this version and with the Exodus file that I create for the South America, and I've gone through from beginning to end, and it has the step-by-step commands that worked for this tag alpha OAA. And there's the refinement map for that. There's the Exodus file, and then there's some other files that we probably won't talk about. Yeah. So one thing. So the reason I have this here. So when users create their grids, I always encourage them to go through and follow these step-by-step commands, and with this grid. In this example, because if it doesn't work, then there's something that was wrong along the way. If it does work and then you have trouble with a grid that you did, then there's probably something wrong. You have something with your grid that is maybe having difficulty. But if you go through these commands with this Exodus file from beginning to end, everything should work. And if it doesn't, then usually it's because people have, they're running the commands. Some of these commands have to be run on Casper, some on Cheyenne. And usually it's because they don't have the right modules loaded, or they're running on the wrong machine. And if you go through these step-by-step guides, you can uncover those problems. So once you go through all this, you will create a repository that will contain all of the files that you have, and it'll have this structure like this. And of course, the grids and maps directories are now obsolete. So you'll just have the other remaining directories when you're done. Containing your topography, your land data. I'm sorry, that is wrong. I'll have to fix that. I meant to point to domains. It should be domains and maps. I apologize for the typo. It was a late night. So the naming convention for your grid, the way we follow it is the first part, NE0 NP4. That is required at the beginning. That is how CSM identifies that it's dealing with a variable resolution grid. So that has to be at the beginning. The middle part is the unique name that you want to assign to your grid. And then the trailing part is the way we kind of identify what your resolution of that grid is. So NE30 is going to be referred to your base resolution. And then the X4 specifies what your refinement region, how the resolution of your refinement region. So the first step is you have to go through and build your executables that you're going to need. So you go through the first section of the notes file, goes through checking out the model and getting that set up. And I think everyone probably knows how to do that, so I skipped that part. But the second section is you have to go through and build your executables. So it goes through, you go into Casper here, for example, and you go into your VRM editor, you load this module and run qmake and then make, and then the program will build. There's a lot of warnings and such as that, but that's just, the C compiler complaining about a lot of things that, I don't know, maybe it shouldn't complain about some of them. And then once you do that, you have that program, it's built and it's ready to run. You can run it on Casper. Did I skip over the part? I'm gonna back up here. Yeah, I skipped over this line. So to run on Casper, you can run, just doing through SSH, and you run the command and it will come up and it'll go through, it'll tunnel its way through the X windows. but it's a little bit slower. And so this first slide here shows the how you can run the editor using a VNC remote desktop, and you get it's much more responsive when you run it if you're running on Casper, or if you're just running on your local machine, then you just go ahead and go through the process and create your Exodus file, and then just copy it up to Cheyenne for the rest of the processing. All right, so you build that editor, and then if you're going to do, if you're interested in doing manual editing and running the command line program, you will go through and go ahead and issue the make command to build that program at this point here. You just make, and then you tell it the file, the make file is in there, is make file create VRM grid. And then once you do that, you can run the command with no arguments, and it will give you a list of its usage and requirements. Okay, so then you have to build the control volumes. This program takes the Exodus file and puts in all of the information that's needed for areas of elements and stuff like that and creates your script file and your latlon file as well. So you go in there, module list. So this is the list of modules I had loaded. I loaded the GNU compiler, showed this here. So if you go through commit this process, this is what you should see, and then you type make, and it builds it, and then that will work. And then of course go back to Intel for their next step. In the CSM tag, you're going to have to go through and build the tool, the make surf data map program. So you go down to wherever you have your tag, and you have to go into the component CLM tools directory here. Go through these steps, load these modules, and then set these environment variables, gmake, and then the program is ready to go. Once you're done there, you have to go into and build interpick. And so then you go through, and that's in the CAM tools directory, and you go through and you load these modules and type gmake, and then that part's ready to go. Now, for creating the grid, the process that we go through is there's three programs that are available. Squadron is the original command line program, and then the VRM editor and create VRM grid are based upon Squadron. They're just a layer on top of that program. The VRM editor gives you a graphical user interface, and then the create VRM grid is just a command line interface. And the reason it's not just Squadron is because one of the main differences between Squadron and the editor is the way rotations are handled. So in Squadron, you refine a region, and then you rotate that face over wherever you want your refinement to be. The VRM editor does it the other way around. You rotate you rotate your grid first and then edit it, and so you center your cube face over the region that you're interested in refining, and then you do your refinement with that on that rotated grid. But in all the cases, Squadron takes a PNG file, and VRM editor edits a reference map. But in each case, what it's doing is it has a rectangular grid of basically values between 0 and 1. And 1 determines the highest refinement level. 0 is your base grid resolution. And it takes that grid of on a lat-long grid, and for each element in your cube, it takes an average of the 4 corner points, and whatever the average value it gets, that's what it determines for a discrete refinement level. So we're editing a continuous map between 0 and 1, but what actually generates the grid is a discrete grid map that has values that are that go from 0 to whatever the refinement level is being applied. So in each of these cases, though, we're creating the NE part of the grid. That's so we have the NE part, that's the number of elements on a cube face. So for any 30, there's 30 by 30 on each cube face. And then the NP part, so that's what we're editing. The NP part is where we add a a GLL grid on top of that. So there's, it's a higher resolution grid. And so we're just doing the base part at this point when we create this grid. So for Squadron, there's, you can just run the command without any arguments, and it lists out its options here. And then when you run that based off of a PNG file, it creates a text file with the refinement levels. And this is an example here that shows it here. And then the way the Squadron runs is you go through, you edit this file. So in the case here, we change those 1s to 2s to kind of clean up the corners of the refinement region. And then maybe in the green ovals, we change those from 0s to 1s to kind of make a larger halo. And then once you edit that file, you rerun it, and then just set your load CSM Refinement Map argument here to true, and it will read this file and then generate the final Exodus file based off of your edited file. Adam will talk about this in a little bit here. And so actually, Adam, maybe we should do this now, because I think that, this is where I put it in the file. So
okay.
no, actually, no, I guess I'm sorry. I kind of have this, the Squadron is here, and then the create editors on the other side of a bunch of slides. So sorry, I guess I should have coordinated this better for you. So
just let me know when, man.
Yeah. All right. So we'll go through the VRM editor, and then we'll pick that up on the other side. But Adam will talk about, he'll show this again. So the layout of how you find your refined region, it's easy to find based off of line numbers in the file. And Adam will talk about that in a little bit. So the VRM editor it's a graphical user interface, as I said, and we're going to go through and create values of 1 here, red is 1, and then clear, transparent is 0. And so when you have your regions of 1 here, you create this region, then this is going to be where your refined grid is. There's a tools menu over here that has your editor options, and you then has the options for that are used for the Squadron. And then there's some display options that you can change. You can change how your display appears in there. And then down at the bottom, once you create a grid, there's some quality information at the bottom here that goes through your grid, and it finds the extremes of arc length, angles, and area. And in each of those cases, it tells you what the min and max are, and then it gives the lat and long of the first occurrence of that. If there's more than one, it just shows you the first one. So if you're having problems with the grid, maybe the angle is too sharp or too wide open, then you can look in your grid based off lat long, find that, and kind of look and see what the problem is and help you debug it. So as I said, so your tools over here, the VRM, these are all the options that go to Squadron, and you have your base resolution, longitude, shift, rotate X, rotate Y are the Euler angles for your rotating your grid, X, Y, and Z. You have a refinement type, qubit or locon, the level of refinement, how many levels of refinement you're going to apply. Then there's smoothing options. And then these are just in there for because there were interfaces for Squadron, but we never use any of these. There's an edit tab that you go through, and there's a Polygon Editor and a Rectangle Editor, and it's a grid smoothing option and reset. And these are what we use to create our refined region. And then there's the Display tab, has ways of turning on and off your refinement map. You can toggle your grid on and off and show the variable resolution or not. So it gives you a way to control your display. There's an option in there for reading in a file to, so in this case here, we have a region that's kind of defined by the, apparent or the frequency of storm tracks. And so if you wanted to have a region where it was kind of based off of some kind of physical domain that you want to look at, you can create a file that has, kind of outlines that region based off of that variability. And then you can use that as a guide for creating your grid. So it doesn't affect your grid. It's just something you can put up and use as a guide for when you're drawing and creating your domains. So in this case here, just kind of created a domain that went around those storm tracks, and then, create the grid for that. And then one thing that is difficult for the VRM editor is when you're dealing with a polar grid, because it kind of has a lat long interface. So when you're editing at the grids over the pole, it can be, kind of cumbersome to do that, but there's always a way to do it. It just may not be as straightforward. So in this case here, I showed like, okay, we want to have a refinement over the pole. So we set up a refinement map with maximum at the pole, and kind of tapers off with latitude. And then, there we go. So from that map, you run the program, and then you can't really display on the grid, but in the addition, the reference material, or so there's a program in there that will take the your Exodus file, and you can graph it. It's an NCL program, so you can look at things over the pole. Now, when we're editing these maps, and you have a number of refinement levels, you have to kind of do some thinking about what value you're going to set to define each domain. So if we have an NE30 grid and we want a NE240 refinement, and we want to have different halos and stuff like that, we need to set the levels, for each resolution accordingly. So in this case here, values that are above 0.83 will basically round up and become the NE240 domain. And when the values average out to in between 8.83 and 0.5, that will be your NE120 domain, and so forth down the road. So, when you're editing and creating your map, you need to, when you set your refinement map level, you need to kind of do some thinking about ahead of time about what value are you going to set for that. So, for the resolution that you want in that area.
If I can just jump in,
yeah.
I would say this is a pretty important step if you're going to be using this graphical user interface that Pat made, that you should get out pen and paper, and you should compute where these boundaries are, just like this, because when you start setting the values in the Polygon editor, you're going to want to use these boldface R values to be able to manipulate the software effectively.
Yes. Yeah.
Okay, that's it. Just wanted to highlight that.
Yeah. So yeah, and so in this case here, this is a zoomed in version of the previous polar grid. And so I say, okay, so we want to, instead of having that refinement go all, from just over the pole, we want to have an embedded higher resolution region here, like over at Greenland. So you take the Polygon editor, trace out the region around Greenland here, set the values to, in this case here, 0.82, because we want it to be, this is going to be our high resolution region. And then we apply some smoothing to get rid of kind of the sharp edges and generate our grid. And then, so this is what it looks like, in the editor. But then if we, use our utility programs, we can draw it, and this is what it actually, this is the region we defined here. Not necessarily that this is a good region, but this is just, it illustrates how you set your values, and you have to kind of know what the value is if you want to define this domain here. So you need to know what to set the R value to. So, so for the new features here, there's the Ref Map NCL program that I mentioned earlier. So you go through that, that's the program that's in there. You just go through that NCL program, and I have it, just uncomment out. So the default resolution is 360 by 180. And then if you go through and you have a grid that's rotated, and this is an example on the left here of the default resolution, and you have this kind of aliasing effect on the side here. And then, these little aliases will cause, maybe this element here to round up to the wrong level. And so maybe you want some fine control over that. So if you change over to, in this case here, it's the 1440 by 720 resolution. So the same domain, you can reduce that aliasing by increasing the resolution. One caveat here is the 2880 by 1440 resolution When I run this on my laptop, this fails. It'll work on Casper, but it will fail on my laptop. And it's because I'm using automatic arrays. I didn't do a memory allocation for this. So I think if maybe I could set like ulimit higher or something like that, make it work. But just the point here is that if you try and make a really high resolution reference map to do your editing, then it may not work on your laptop unless you it may not be your laptop might not have enough for it. But like on my workstation and Casper, yeah, you can go to higher resolutions. So yeah, and when you excuse me. So when you're creating a grid, there's two different refinement types. There's qubit, and that uses a set of templates the size of one of the lower resolution grids for the transition. So the templates I kind of have drawn out here. So we have the high resolution region here, and then the next lower resolution. And these are the templates that are used to connect those two. For Locon, the set of templates span 2x2 elements of the lower resolution grid to transition to the higher resolution. Generally, Locon is what we want to use because you want to have that transition spread out as much as possible. But there are instances maybe where qubit is more appropriate for your grid. So in this case here, it shows how these different templates connect the higher resolution to a lower resolution grid over a little bit longer transition zone. Okay, so let's kind of move this in here. All right, so this is our editor here, and 45. Okay, so I'm going pretty slow. So we'll, once you start out your program, this is what it looks like. You have your display options here, as I said, and then your VRM editor here. Cube squared is, we always leave this here. If you go to icosahedral, it'll probably crash. And this program was a little bit unstable for a while. And what I found was typically when you're going through the editing process, you go here, you click on this tab, and you go down here to click or generate mesh, and the focus will go across here and then rotate that onto here, and it'll cause a program to crash. And so I think the program should be a lot more stable than it has been in the past, because that was seen a major cause of the problem. But there are instances, combinations of refinement level and smoothing options that still fail, but that's not as frequent. So if we just click on generate bar mesh with nothing there, it'll generate. This is the default grid, and then we can rotate it to different ways. So if we're going to focus here maybe on South America, so we should the arrow keys up, down, left, right are used to go left and right and up and down. And if you're trying to use these arrow keys and move them around and nothing's happening, you have to click in here to get the focus in this map, and then it will work. Your wheel mouse controls, so you can zoom in and zoom out with your wheel. On a Mac, it's you do the pinching thing. If you have a 2-button thing, I'm not sure how you do it on a 2-button mouse, but yeah, I'm sure people that have those know how to do that. So if we kind of focus in on South America here, and then we want to rotate, say, .30 degrees here. So just go ahead and generate that. So we see it rotates in longitude, and then we want to go say X to 21. So this puts, say, South America kind of in the center of this cube face. So this is kind of where we always start. We want to have our cube, our region of refinement. We want to center on a cube face as best we can, and because once you start crossing these boundaries, then then your grid's going to, that's good. The cases where the grid's going to be problematic. So if we go through edit, go into the editor, we have Polygon Editor. Now it starts out in its default location. The reset button here always takes the Polygon Editor and centers it on your view at the time. This is a distinction from this reset here. This reset here zeroes out your reference map. So if you're just like, I'm going to start over, you zero the reference map here. and that, sets all the values to 0. So if you want to have like a domain over South America, there's only these 8 control points for this polygon. So like in a big domain like this, you're not going to necessarily be able to do it all in one with these 8 points, because you kind of want to have your refinement follow these grid lines as best as possible, because that will give you the best results. So what you have to do is kind of go through and go ahead and set that up, apply, and then, all right, so now I want to you basically have to build it up with different applications of this polygon here. So you go through there and apply, and just go ahead and exit. When you get done, so this is obviously not going to be the refinement region I want, but I just want to show it. So you want to, when you get exit edit mode, you say yes. Now that it goes away, but that value is in there. So if you go display, you can turn it on and look at it if you want to. But then you go to VRM editor. So I want a NE30 resolution, maybe about low con. Just go up to 2, and then you can have spring smoothing, generate your mesh. And so you have like a pretty messy looking refinement region here. And this is just, I did this, so there's an example. So this is a grid that we would not want. So in general, we want a grid that kind of, if it looks good, then it probably behaves good numerically. So as a general rule of thumb, if a grid looks, neat and clean in terms of, its appearance on the cube, then it's generally going to have better numerical properties. So we don't like this area here. So if we go through and edit it, it remembers where we were, so we can zoom in and say, okay, I want to get rid of that situation there. So I just go ahead and say, okay, apply, and then exit. Yes, VRM editor, generate. And we can clean it up that way. Now in this case here, let's just say we want to get rid of that area there. So we go back to the editor here. In this case here, so I'll just go ahead and reset this. I kind of want to get rid of this here, this little sliver here. So these are the options here. So the option here is you have a fill max value, a fill min value, or fill all. So what this does is fill max is, if I have this rectangle editor and I have this value set here, in this region here, it's going to set the value to the maximum of whatever's in the map or whatever's in my Polygon editor setting here. Fill min does the opposite. It takes a minimum value, and then fill all just says, I don't care. I just want everything in this rectangle here to be set to this value. So if you want to get rid of that little side lobe there, so we go over here and say, all right, I want to subtract this off. So we just kind of drag out some region here. We don't necessarily care about this over here. All we want to do is say that, and then we set this value down here to 0, apply, say still fill max. So it says, okay, the max was 1, so it stayed at that. So I say, all right, fill the min value, apply, and it just trims that off. So if it's okay, exit, go here, go to the editor, and generate the mesh, we can clean that up. So this is the editing process. You can go through and fix little problems and make your grid nice and uniform looking. Now, one thing, so smoothing is something that, there's cases where it's good and cases maybe where it's not so applicable. And typically, if you look here, and this isn't a good example, but I'll show it anyway. So in this kind of corner region here, we have this kind of discrete jump in the high resolution region. You have this corner template here. These little pieces here can be smaller than your high resolution region, and the size of the smallest element here is going to determine your CFL limits. So smoothing can help undo that. So if we go here, so smoothing none, and maybe just show an example. So we watch this element here, see how that element is kind of smaller than this element here. So if we smooth it with some smoothing, we can kind of, make it a little bit bigger and equalize the areas. And so we can, get better numerical properties there. But in general, we don't want to have this kind of jump here. We just want to have nice uniform refinements that go along the default grid lines. But, some cases you can't avoid this. And so the spring smoothing can help you out there. Okay, so let's just go ahead and, so on the actions menu here, there's a, this is, I'm going to read this, I want to read in a refinement map, and I'm just going to go to desktop. So I just read in the refinement map that I've gone through the process of cleaning up the whole area there. So if I show it, this is what kind of the final refinement map for South America grid. And this is what we're going to use for, this is what I use for the rest of the demonstration. This is the grid that I use for testing out all of the scripts. So go ahead and generate the variable mesh for that. Let me see here. It's a nice uniform region, and this is what you want to have it look like in the end. So kind of running long on time. So if we go to the actions here, there's a new option here. This is the other new option of read refinement grid or write refinement grid. So this, what this does is, I didn't show this. So this green area, this is the actual discrete refinement grid that is used to generate for your final grid. And so if you had in there a blemish, let's just make one. Oh, so if you had a blemish in there like this right here, and this is just an extreme example, or if you wanted to add a perimeter around this file, the alternate method for fixing this is you can write the refinement grid. So this refinement grid, if you look, it's kind of sticks out here, has a discrete structure here. Maybe this is the way to show it. So if we go here, go to the base resolution, this kind of shows this area here has, the discrete value here is wrong, and we want to get rid of it. Or if you want to add a perimeter around the side, editing and adding the perimeter, depending on your region, can be a tedious process with the Refinement Map editor. So what you do there is once you have it done, you write your refinement grid, it comes up, and you save this file is going to be a text file, so you save it, as a text file, and then save your Exodus file as well. So I will cancel that. So you go through the process, save your Exodus file, save the refinement grid, and then once you get that, then you can go through and manually edit and fix problems like this manually. And so, okay, Adam, so I'll stop sharing now, and you can pick up at that point.
Yeah, okay, it seems like a natural point to switch to showing you this functionality. So I'm going to share my screen. Let's see. So to be clear, what we're doing here is if you're just not getting anywhere with this Polygon Editor and making a pretty grid, and there's just some blemishes that you just can't seem to get rid of with the Polygon Editor, then this is when you lose patience and you decide to go in manually and find that point and change it. So I'm going to show you an example of how you clean up a blemished grid. And I'm going to start from the beginning here. I'm going to open up this GUI using Tiger VNC. So this is a slide that that Pat showed on how you would open up the GUI if you were on Cheyenne or Casper. And you can't do it with, you could do it with SSH, but it's going to be extremely slow. And so you want to use this Tiger VNC option to open up the editor on Cheyenne. So here I am on Cheyenne. Well, let's put, yeah, okay. Here I am on Cheyenne. I'm going to execute this command. This is, I know you guys can't see this, but there is a thing in my way. Okay. So I'm executing this command down here. And one of the arguments is the project code. I can never remember my project codes by heart, so I'm just going to execute it with this generic project, and it's going to pitch a fit that I didn't put in the right project account. It did not pitch a fit, which is, I guess project is a okay. Project is a variable, and it gives me my project account. All right. So anyways, you execute that command and you want to use this SSH tunneling method. And so you copy that and you go into a new terminal window. And you're going to SSH using that command. Hoping I can keep this to 10 minutes, Pat. I'm going to do my best. And there it goes. Now it's giving me credentials for the Tiger VNC. And so I have already downloaded Tiger VNC. So I'm going to open it up. It's going to ask me for the server, and that is provided here. I'm going to paste that in there. Connect. Now it wants a password. Well, that's given right here. And looky that. It opened up basically this Tiger VNC. So I'm going to start from scratch. I'm going to open up a terminal window. Okay. And so now I'm in Casper in this Tiger VNC tunneling method. So I'm going to open up the GUI. Okay, so VRM editor. I already have it installed, so I'm just going to execute it. There we go. So I'm just going to make a really ugly grid, and we're going to trim it up using this new method. So first thing, I just like to generate the base resolution grid. Give me something to work with here. I'm going to go into the Polygon Editor. Okay. I'm going to zoom in. You can just scroll down to zoom in. And I'm going to make an ugly grid. So I'm going to try to keep this refinement to just one panel. That's the goal for practical reasons and for sort of OCD, making things look clean reasons. So I'm going to try to keep this polygon just span one panel. Okay, I'm sort of on purpose messing it up. All right, and I'm just going to apply a value of 1 to everywhere. I'm going to exit edit mode. It disappears, but then you can always just bring it back by toggling on Refinement Map under Display. Okay, now I'm going to set the parameters for refining the grid. I'm going to use locon. I'm going to do two doubling of resolutions. So refine level equals 2. not going to bother rotating the grid. I'm not going to smooth or anything like that. I'm just going to generate it like this. And what we have is a ugly grid. If I can figure out how to zoom out. Okay. So there's my ugly grid, and I'm going to clean it up manually because I'm just not making any progress with this Polygon editor. So you want to do three things. First thing you want to do is you want to write the Exodus file. And the only reason I'm doing it is because it actually memorializes all of your settings into the Exodus file, and you're going to need that information to run the command line version of this software. So writing Exodus file, I'm going to write it into this directory. I'm going to call this grid panel Exodus. No, I don't know why these files are called Exodus after a Bob Marley song, but it's not something I'm complaining about either. Save that. Now I want to save out the refinement grid. Now this is the text file that we're going to end up manipulating. I'm going to call it EQP Refine Map file .dat or .text, whatever you want. And lastly, I'm going to write out basically what is equivalent to what you would feed into Squadron is the PNG file. It's a sort of a picture. It's the green polygon picture that Patrick has shown. So I'm going to save that refinement map. And I'm going to call it let's just call it refine map and .nc. So it needs to be an NC file. Okay, so we've got three files that we saved. So now we're going to go into I'm just going to go into Casper or Glade, whatever you want to use. Okay, here's sort of the main directory. The editor and stuff are in there. I'm going to go into grids where I saved everything. Grids. And here are the three files. And what we want to do is we want to start feeding in these files to the command line version of VRM Editor. So I'm going to show you, this is everything in the source directory for VRM Editor. So this is how you would open up the GUI. We don't want to open up the GUI. We want to execute the command line version called create VRM Grid. And so the first thing you want to do when you are working with a command line software package and you don't even know anything about it and what the arguments are that it needs, you run it either with no arguments or a -- help. And that'll tell you the things that you need to feed into this command line to spit out a nice Exodus file. So for example, refine level, I know the value is 2 because I just did it, but let's say I can't remember it. What I would do then is I would just spit out the metadata from the Exodus file we created, and that Exodus file has the bad grid. So I just did an ncdump-h, and all these VRM underscore variables are the options that you used in the GUI to create the grid. And so I want to know refine level, and that's contained in this variable here, VRM underscore refinement. I will admit that in the future, it would be nice to have these variables be exactly the same as the name of the variables in the command line. So just to remind ourselves what's needed in the command line, well, let me spit out the value of refinement. Okay, spit out the value of 2. And to remember, the arguments we need to provide are here. And so that's going to be this argument. So let's go ahead and start constructing all the arguments to reproduce the bad grid. So refinement type, I'm using locon. Grid type defaults to cube squared. I'm not going to be using any smoothing, and it'll default to none, so that's fine. The base resolution defaults to 30, but good to be explicit about what your base resolution is. Refine level, as we just saw, is the value 2. Tessellate subcells, all this other stuff, all these rotation parameters I did not set. And so at this point, what I need to do is start inputting this refine file. So this is kind of equivalent to the PNG file you would feed into the Squadron command line. And so that refine file is going to be this this thing, probably terribly named Refinement Map, because it's, I tried to make the naming make sense, but it looks like I got things backwards. But the refine file is going to be that netcdf that you saved. The output, I'm just going to call it new mesh.nc. So that's going to be our new Exodus file. And refine cube is the text file. And we're going to go ahead and pop that in there as well. Okay, so I'm going to execute this. And it created new mesh.nc. And so now I just want to plot it and make sure it reproduces the bad grid. And I know there's two Michaels on this call, but one of the Michaels was curious about how you plot these grids. And you know, let's go to the main repo for the Community Mesh Generation Toolkit that contains everything you need for this tutorial. And in VRM diagnostics, there's a bunch of plot scripts here. And this gridplot.ncl is a nice, useful plot to plot Exodus files. I believe it was initially created by Paul Ulrich, and it's used quite often. So I have gridplot.ncl in this directory because I was prepared. And I'm going to go ahead, and all you have to do is just set the grid file to the Exodus file and plot it. Okay, let me copy this to my machine and take a look at it. Make sure it looks like the bad grid. Let me close this thing out. I don't think we need it any longer. And open up the PDF. And here is the bad grid. Okay. So what I want to do is my OCD wants to contain all the refinement into one panel. And as you can see, the refinement is bleeding over into neighboring panels. The panel boundary is here. So I want to try to keep all the refinement contained in one panel. I want it to look like a panel, so I don't want these little nudges over here. And so I'm also going to create a buffer zone so that the first time we double our resolution, it gives a little more space for the grid scale flow features to sort of collapse to the grid scale. And then that, you know, the reality is there's features in the model that always collapse to the grid scale. So if the grid is changing underneath it, those features are going to collapse down immediately. And so if you have two doubling of resolutions, that collapsing effect can end up creating spurious grid features due to a bad grid. So you want to have a nice gradual transition zone. And so that's the two things I'm going to do. I'm going to contain this all to one panel. I'm going to make sure I have a nice gradual transition to the higher resolution region. So this .dat file is what we need to look at. And just to prepare you for what it looks like, it's basically a bunch of zeros, meaning these are spectral element grid points, spectral elements that don't have any refinement. There will be some ones. Those are spectral elements that you want to have a doubling of a single doubling of resolution, and then there will be twos in the interior for regions that you want to have two doubling of resolutions. And it's the DAT file is laid out in a pretty logical way. We have 6 panels that make up a cube sphere. And so the DAT file is basically going to just stack all of these panels on top of each other. And so it'll move 5 down below here and move 6 below that. So it'll be just a stack of 6 30 by 30 entries. So let's take a look at that. So here it is. If I go over to the end of the first row, it tells me that there are, well, it says there's 59 columns, but there's a space between each one of these zeros. So there's 30 columns. And then if I go down to row 30, this will be the first cube face. So this is one of the cube faces. And so then there are 6 of these stacked on top of each other. And so that means the size of this file should be have 30 rows times 6, which is equal to 180. And so I'm at the bottom of the file here. And so that's how this is laid out. I'm going to start going back up in this file, and already I'm seeing these spurious ones all over the place and panels I don't want them. And here's the main panel. And then up here, there's some spurious ones as well. So this will just take a minute, but I'm going to go ahead and zero out all these unnecessary ones and panels I don't want to even refine. Okay, that's that. This reminds me of beginning of grad school. This is how I would modify paleoclimate data sets for use in GCMs. Just go in there and manually change things. All right, we're almost done. I admit I didn't expect there to be this many problematic ones. Okay, got some stranglers over here. I think I saw, oh, look at that, there's a random one over there. Okay, scroll down anymore. Ah, there's a couple more there. And then as soon as I get rid of these, we're going to go back up to the panel where I want to refine. And we're going to manipulate that the correct way. Okay, now I'm just getting late. Okay. So here's the panel. And so this is just one, this is the entire equatorial panel. And I can already see there's problems because you don't want to have any non-zero values at the boundaries. That is automatically, at least with Locon, is going to cause bleeding into other panels. And so you need to have zeros around the edges. It's especially problematic on this edge where you actually have 2-level refinement at the boundary. That's definitely going to bleed over to the other panels. So I'm going to go ahead and cheat because I know the answer of what I want these to look like. So I'm going to go ahead and grab that. Grids. Okay, so I'm going to steal it from my Arctic grids. Okay, so here's the right answer. And there's a 2-0 buffer. around the panel edges. So that's the right answer. I'm gonna go back in here and I'm gonna delete this panel altogether, paste in the right answer. And now I'm just gonna make sure I didn't change the file length. I copied it in correctly. Okay, there's still 180 rows, so I didn't add any additional rows. Okay, so that's the right answer. And then all you do is you rerun the command line arguments. So this is what I've modified. And so this is going to take precedent over this refine file, which is the polygon in the GUI picture. So it's going to overwrite this, and it's going to follow entirely what's in this .dat file. Okay, and now I'm going to run grid plot. And we're going to take a look at the new grid we just created. And here it is. Nice, symmetrical refinement contained entirely to one panel. I have a nice 4-element buffer region. And so this is the ideal grid. So just a side note, if you email me with questions about variable resolution and you include a picture of your grid and you don't have buffer regions, I will provide unsolicited advice that you add buffer regions to your grid. Okay, I could talk about why this is important through examples, but we can cross that bridge when we get there, as there's not really enough time to do that right now. So that's how you, when you get frustrated with the Polygon Editor, that's how you fix blemishes. You go in there and you change 1s to 0s to 2s in the .dat file. So feel free to interrupt any questions or anything like that. Otherwise, I'm going to hand it back over to Patrick. Okay, I take the silence to me, and I've explained everything perfectly.
Adam, you did actually, but I do have a question. It's a very simple-minded one. That is, after you've done the refinement of the face, as you showed, for example, can you rotate the grid afterwards rather than having to do it beforehand?
So this is okay. Go ahead, Patrick. You're more.
Yeah. So yeah, that is the distinction between Squadron and the VRM editor, is that the rotations on the editor happen first. Squadron, it happens afterwards. There is a to-do item on my list for making additional options so you can rotate before and after, but you know, I've never gotten time to do that. So for now, yeah, the answer is no. You have to rotate the grid first and then do your edit, or then create your grid for if you're doing the VRM editor. If you want to do it the other way, then you just use the Squadron interface directly if you want to rotate afterwards.
Okay.
Okay. All right, so, all right, we did that. Okay, so we went through, you created the grid. So in the example that everything will, all the rest of the thing will be based on is this SAM grid 01 Exodus file, which was created from the reference map that I showed. And that's available in the documents directory. Yes, along with this list of commands, of notes. So, and this is what Adam went through here. So this is the refine cube option for using the create VRM grid. And as Adam showed, the VRM editor settings are all embedded in the Exodus file. So you can just use NC dump to get them back. Probably in the future, you know, I will change the create VRM grid so that it just reads in the Exodus file directly, so you don't have to worry about figuring out how to set all the arguments, but that's also on the to-do list. So in terms of best practices, so this is a summary of best practices when making a refined grid. So the refined regions whose boundaries are aligned with the spectral element grid tend to behave better. Regions that look good, have a nice uniform symmetric appearance, tend to behave better numerically. Locon in general should be used instead of qubit. Spring smoothing, this must be an old slides, Adam. We took that out. So spring smoothing can help, but it's not necessarily to use it all the time. Convex regions tend to behave better than numerically compared to concave regions. Concave regions are usually the source of most numerical problems. And if you're having trouble with the grid, it needs a lot of subcycling and is in order to run, and there's probably a problem with your grid that you should go back and redo your grid and make some adjustments. In the long run, you're better off iterating with variations of your grid if you're having numerical problems to get the best performance. So that way you don't have to waste a lot of time running a grid that's inefficient. Refinement regions that are with boundaries aligned to the rectangular spectral element grids didn't behave better numerically, yes. Okay, this is a repeat. So that other slide was left over, I guess. So this is all repeat. Yeah, so try and center the refinement region to the cube face, and then avoid a lot of aggressive refinement at the edges of the cube faces. So if you're transitioning from a high resolution to a low resolution in the neighborhood of the base cube face, then you're probably going to have some troubles with that. And if you're making a small region, you may want to start with a NE60 grid instead of NE30. The Polygon Editor, the vertices can't be increased from a number of 8. Like I said, you just have to use the Polygon Editor and kind of iteratively build up a region if it's a large region. And so sometimes, sometimes rather than doing editing refinement, if you have just a small blemish on the side of your refinement region, sometimes just a small rotational shift can make that go away, just to get, you just change it by 1/10 of a degree and it'll go away, and then you don't have to worry about, doing any editing and iteration on it. It doesn't crash as often, but it's a good idea to save the refinement map frequently, because if it does crash, you can always just read in and restart where you left off. But if you've done a lot of work and all of a sudden the program crashes and you have to start from the beginning, it can be a bit frustrating. And it's worth saying twice that if you're having trouble with the grid and needs a lot of subcycling settings to make it run, a lot of high values of end split, then you probably have a problem with your grid, and you should look at it and maybe try some variations of that grid. So these are some examples. We'll just kind of go through these quickly because we're short on time. So this, and you can look at the PowerPoint afterwards. So these are just different examples of grids. This is a grid here, for example, that doesn't have a nice halo around it, so maybe isn't going to be so nice numerically. And the grid on the right shows a nice final grid where you have very large transition regions, and it's a very neat looking grid. So yeah, you can have the corners. You want to kind of have those. You want to have these areas in the corners. You want to round, make those nice. You want to have a nice halo here, and you look for little blemishes like that, because this is where you're going to have problems numerically when you have little protrusions like that. This one has good buffer zones, but it crosses the edge of a cube face, and so it's going to be a problematic grid. And if you have multiple regions and they kind of bump into each other, then that's going to be, you can have some trouble with that as well. So this would be a case where maybe you want a qubit refinement kind of isolates your regions, and maybe that would be a better option. So when we're creating the grids, there's a number of grids that we make. So the first one we make is the Exodus grid, and that's with our editor. And then from there, we're going to use our gen control volumes. That's going to create a script file and a lat/lon file. The script file contains the spectral element grid points that are overlaid on each element, and has the polygonal regions associated with each point and the corresponding area weight for each point. and that's what is used in the model. The lat-lon is just has the lat-lon grids, and this is what you would typically see in a history file. One difference between this and the history file is it has connectivity information embedded in there as well. So if you want to graph your history file, you can get that connectivity information from the lat-lon file and pass it on to a graphing program, and you can be able to graph your grids and look at your data more readily. Hopefully one day we'll have the connectivity information embedded in the history files, but it's not right now. And the last file is a mesh file that you would create, and that's an enhanced script file that's used for ESMF for mapping functions, and that's what the foundation of everything is moving forward is. So we create a mesh file as well. So once we have we've done that, we've created those grids and all those grid files. We need to create a repo directory. So this is where we're going to find some spot, and this is where we're going to put our grid, all the grid information, and all the initial files and everything, configuration files that are associated with that grid. And in general, my rule of thumb is I name the directory after the grid. So in this case here, it's NE0, NP4, SAMGrid 01, NE30 by 4. And create that directory, put your grid files, create a grid subdirectory in there, and then you put in your Exodus file there. I also always put in my ref map that I used for editing in there as well, just for future use. If you don't have that, the reference map is actually embedded in the Exodus file. So if you're lost and you're like, I really wish I had that refinement map that I edited, you can recover it from the Exodus file. It's embedded in there with the VRM settings as well. So once we have our Exodus file, we go through and we run gen control volumes. And all you'd have to do there is we've already built it. You just edit the input name list. You tell it the path to your grid, and then you give it the root name of your grid. So you see here, it's SAMGrid NE30 by 4. And so it's kind of like, this part of you don't give it the NE0 part. So this grid name here. Run that, and then if you look in your directory, in your repository, now there's a script file, a lat-lon file, as well as the 2 files that you already have in there. And from this point here, we need to go through and look at our lat-lon file and get the number of columns out of that. So do an NC dump, get that number of columns because you need that number. Then you go through and you set a series of environment variables with your tag, your path, your grid, basically the name of your grid, and a grid tag name, your number of columns that you got there, and then you set a date here. Generally, when the files are created by the scripts, a date is tagged onto it so that we keep track of when the file was created. This has been a problem in the past. If you're if you have all your grids and they all have a certain date on it, and then you go back and create a new grid on the next day, it would end up with a different date name on it. And then it would cause a lot of problems with the configuration scripts because you'd have to go through and find that and set different dates for all the different files. So we set the VRM date in the environment variable here to one particular date that's associated with the creation of these files. And then that is used to appended to all the files so that the configuration scripts can find all the right files. So then we create the mesh file and just go through in the gen ESMF. From this point forward, once we set our environment variables, each of these directories, there's a make, capital make underscore, and then some name, kind of a script. So you just run that script and then it generates, the script that actually you run to do what you need to do. In this case here, you run the make ESMF script CSH, and then it generates a script, gen ESMF SAMGrid NE30. So basically it sticks your grid name in there and creates a script, and then you run this command to actually generate your mesh file. When you run this make command here, I don't have it in these examples here. The output from this command here actually gives you the list of commands that you need to run from that point forward. So, if you're prone to typos, you can just mouse in those commands and run them that way. So in this case here, this command here would have been on the output. So you just mouse it in, run it, and go. So now if you look in your grids directory, you have a mesh file as well as your other grids. And then from that point forward, we're going to move into the generating of the data sets. And so this gen mapping, gen domain, this pink here, these are all obsolete. So we're just not going to worry about these anymore. So you go into directly into creating your land surface data. You go to the gen directory for that, run your make script here. It lists out the commands that you need to run. So you CD to there. And in this case here, you have to edit the script and put in a project number. And then you submit that, and then it takes about an hour to run for this grid. And then when you get done, if you look in your repository, you have a CLM surfdat 50 directory. And then there is your land surface data. And then, this becomes kind of monotonous at this point. It's the same process over and over again. You go into each of these gen directories, you run your make script, and then you do the commands that it says there, and it generates. So you go through CAM NC data, and then all of a sudden you have an INC data that has your initialization, your CAMI file. And you go to ATM surf, run the commands, and now you have a ATM surf directory with the file that you need from there. You go into gen topo. Now gen topo, there's two different ways here. There's the true topography, or you can interpolate. We always want you to run the true topography, but there's an option there if you just want to, I just want something quick and I want to take a long time doing it. You can just interpolate a NE120 topography, generate that topography, and then you can just do some testing and get your case, your grid up and running, and then go back and generate the true topography afterwards. So in that case there, when you run that, you'll have a topo directory here, and it will have an interpolated topography option available. For true topography, you have to go through and you go in that same directory in gen topo. There should be, if it's not made, then make a topo directory, and then take out the true topography source data from the GitHub, CD to that directory, and then go over to Casper, and then I always make a backup copy of any files that I'm going to make changes to. So I make a backup copy of the experiment settings.make, and then I edit that, and not typically I use something like the Arctic grid or something like that, or one of the settings that's already there as a guide, and then make modifications for my grid. In this case here, I think I use the Arctic grid. And so then you comment out at the beginning whatever the export case is, and you add your grid. And then down below, you add the settings for that grid. So in this case here, it's a SAM grid 30x4 case. So these are the settings here, and you set your grid name and the path to your script file in your repository. And then you have to make sure that this, that's going to change the slide. This RR fact max this 4 needs to match your refinement level here. So this is something you have to do there. But then other than that, all these other settings are just kind of what is, typically for, for one of these grids. And then you get done with that, you load the GNU compiler and you type in make, and then an hour and a half later, you have a topography file that's been generated. And once it's generated, you go to your cube to target. There's a directory cube to target. You go to the output there. The file that it created is in there, and you have to manually copy that to your repository, and then make sure you append the corresponding date at the end of the file name, so it matches all the other files. There's going to be, expect the process for creating this true topography to change in the near future. Adam and Peter and Julio are working to revise and revamp this so that, because there's was a limitation when you got down to around 3 kilometers, you'd have some problems. We're fixing that, and they're streamlining the whole process. And so it'll be greatly simplified, and all these problems will be addressed. So this procedure here is going to change in the near future. So you just have to adapt to that, and as it comes along, and we'll provide documentation to show people how to go through the new way of doing things. So when you're done at this point here, now I have the obsolete pointed to the right place. So the domains and maps files, those won't be in there because they're obsolete. So you'll have your repository, and then there's going to be the directory you created with SAMGrid, and there's going to be all these files here and that you need. In that case, there everything's generated. And now we go to installing the grid. At this point, we have to have an additional environment variable, VRM topo tag, and this is where you set which topography file you're going to use. And so if you set topo tag to BLIN, it will use the interpolated version. And if you set it to this thing here that just tells you exactly what's going on with your topography, then it will use the true topography. So that's what I did here. And then in this case here, the install grids, now the directory is new OPSI tags. And the old one, and the other ones are still there. So I changed the directory. So there's an MCT tags, which has the installation for MCT grids. And then there's a new OPSI directory, new OPSI tags, and that is for installing the new OPSI grids that we're using now on. So you go into that directory, do the usual type make install scripts, SH. And in this case here, you want to edit the resulting grid so that you put in a grid description. So you just put in a text description for your grid. So this is a rotated NE30 base grid with an A120 refinement or South America. Change that, run that, and then what that does is it installs the shell commands, config grids, user nameless cam, and user NLCLM. So these are the configuration files that you need to create a new case. And once that is done, your repository is complete in the sense of all the files have been constructed. So you go through and you create a new case. You put in your grid here. And so you have your grid name here on the back end here, MT12. You can just use that. There's different domains for that, but just use MT12 for now. And then your comp set. And then you add in this flag at the end, user mods directory, and then you point this to where you put your repository. In this case here, it would be samgrid01, NE30 by 4. And then you type in the command and it will build your case and or it'll create your case. Go into your directory, do a setup, set your wall time to, I just put 45 minutes, it's more than enough time. And then see that, check your time step here. So in that, in your shell commands here, it sets the PE layout and the time step. So, those are going to be the values, the default values are set, but this is where you have to set your time. You'll change these values to set your time step that you're going to use to run with. I think for this case here, you just use whatever comes in, it'll work. And then build it and run it. And for this case here, it should run just fine with the default settings for the SAMGrid 01. And from that point forward, once you have, at this point here, then the question is, what's going to take to get a stable 5-day run? So as I said, for SAMGrid, the default value should work, but you're going to have to go through an iterative process setting those values and trying to get the optimum value for the settings, because you don't want it to be, unstable. Obviously you don't want that. So you want to have values that are going to work, but you don't want them to have them set so you're wasting a lot of computational resources subcycling too much, that your grid will run fine on lower levels or lower values that run more efficiently. So the way these settings are structured is, first thing is the PE layout. You have to make sure you have enough processors and memory for your grid. And then, you get to a really high resolution grid, then you're gonna have to play around with this and find out how many processors you need. In some cases, you can run out of memory, and so you have to do some other settings. But outside of that, the main setting is your time step with ATM NCPL. And then you have the split values that are in your user nameless cam. And so you have to set these values here, and you generally start with NSplit and work your way down. But you can have different cases where you need to set the hypervid subcycle, for example, to different values for it to run stably. And okay, so So you have to go through this iterative process of establishing defaults. So in the text file here kind of gives a good guide for, how to go through that process. But you have to go through and make sure that your grid is stable. So in the ATM log file, there's output there that lets you know whether you're going to, if you satisfy the CFL constraints or not. And then you go through and change your ATM, you change your time step first, work your way that way from those. And then, in your shell commands here, this is where you set it. You change this value here to 144, for example, for a 600 second time step. And then this is where you set your P layout number of tasks. So this is in your shell commands file. And in your user NLCam, these are the values that you're going to kind of iterate on with N split, R split, Q split, your damping at the top, and your hypervis subcycling and scaling. And in the user NLCam, this is where you set your default surface data that you want to use. It puts both in there that it created, and it just kind of defaults to 1850. But if you want to use the other one, you edit and then comment out the other option. So the interpolated initial file for the 5-day run is invariably out of balance, and so it will require generally higher settings. Maybe not always, but you might have to have an N split that's higher than a good file, a well-tuned file. So after you go through and get your 5-day case running, it might be a good idea to take that, create a new initial file, put that in your repository, and then use that as your default, and then iterate and see if you can adjust your splits down a little bit more. But once you're done with that, then in this process, you go back in your repository and edit those files, because that's where your defaults are going to be. So once you figure out what the N split that's going to work for you is, go back to your repository, edit the user NLCam file in there, and set that value for your default. So that way, every time you create a new case, your default values are already set there. So once you get to that point there, you're kind of like, okay, now you're in business, you're ready to go. So if you want to do more scientific runs, or you want to run cam, you have to do a little bit more work if you want to do nudging as well. So in that case there, you might have to spin up a surface file or a land file, and then put that in your repository, and then change your user NLCam to use that as your default. And so you go through and once you get it set up, you always go back and set your default values. These are a number of resources that for looking up stuff, and so you can look at those places for more information. I have here, so the kind of go through the steps for doing the additional things for processing emissions and stuff like that, and processing the nudging data. We'll just go through these quickly because it's we're running late, and it's kind of the same process. You go through and you generate your files, put them somewhere, and then tell your program where to find it, and then just use them. Okay, so that's that. So the last thing we want to talk about is maintaining your repository. And so, as I said at the beginning, when we first started out, we were kind of in the MCT era where there weren't a lot of differences, not a lot of changes. Everything was very stable. But as we all know, CSM is always evolving. There's constant stream of new tags coming in, and when substantial changes come along, for example, who knows what we're going to have to change when Derico comes along. We're going to have to expect that there's going to have to be some maintenance that we're going to have to do on our repository. So, CISL in the CSEG group can't do all this work for everyone. So this is on the users that they're going to have their repository. And as time goes on, they're going to have to confront situations where they're going to have to make adjustments and changes to their repository in order to support, the tags that they want to run. So in this case here, so, if you need to update the new default values, or if you want to add a new topography option or a different initial file for the atmosphere or the land, so you update your files there and then set your defaults to use those. And then in this case here, what we're confronting now is if you're a user that has to manage a repository where you have users that want to use the release version, and you have other users that are like, I want the latest version here with the best physics options, then you're going to have a repository that manages both of those cases. So there's a little bit of complexity that you're going to have to contend with. So in this case here, I guess if I was doing it, if I was that situation, the first thing I would do, maybe it's not the best way, but the first thing I would try is if I had to support MCT and nuopsy, is I would have my base grid directory that I created, my repository with all my files there. Then I'd have another grid where I'd basically append MCT to one and nuopsy to the other. And in these directories here, I would just have the config files, the shell commands, and the nameless files that are appropriate for MCT here. And those configuration files that are appropriate to nuopsy here. These files would all point back to these, this directory here where all the data is actually at, because the data is essentially the same between these two options. So just point to there. And then in my new case command, my user mods directory, I would, instead of pointing to this directory here, my grid, if I was using an MCT tag, I would point to this, and it should pick this up and then work just fine. And then other users append nuopsy if they're using a newer tag. So that's kind of what I would try as a first cut if I had to manage a case where I have users that want to use both options. And then, of course, as time goes on, we're going to have Derico come along, and we're going to have to deal with that complexity when it comes. But and it's always whenever you do, you should always, if you do something, I recommend always going through and editing your user NLCam and user CLM files with all the available options in there, but have them all commented out, and then just have the default option uncommented. So that way, when the user does a create new case, if they want to use, say, a different land spin up file, then they just go through and comment out, the one that they want. And then they don't have to go and try and find out, well, where's that file at? What's it called? And they don't have to create that, uncommenting something is easy as opposed to like going and finding the file name and typing it in. So it's just an easier way of doing things. And so I think with that, that's all right. So, and that's what we have here. So if there's any questions, I'm sure we'll hopefully have the answer for them.
We've been having a little conversation in the chat, Pat, but I think everything's all cleared up. If anyone has anything else they want to talk about? I guess I can summarize sort of, was someone about to say something? Okay, I can summarize the discussion as basically being, what if you want to refine a region that exceeds one panel face? And the answer is that's fine. You can do that. We have a couple operational grids that bleed into other panels. The only thing you have to make sure is that you don't put a refinement transition on the panel edge. Okay, so if you're bleeding over, you don't want to change, you don't want to do the transitions right on that panel edge, or it'll break the grid file. One example of this is Brian Medeiros has a grid where he, Pat and Brian worked on this grid for a while, but it refines an equatorial belt across the entire tropics, and so it goes through 4 panels. And as of lately, we've been getting that that is running stably. And it was sort of more important to make sure that you had a sort of a gradual mesh transition rather than worrying about the fact that you're bleeding into other panels. And that we have a very nice scale-aware tensor hyperviscosity operator that allows us the flexibility to bleed over into other panels and to have weirdly shaped refined regions, because it's very smart at what happens when you do weird refinement is you get some elements that are really distorted when, they may be very tall and thin, or who knows, they could look all sorts of crazy. And the tensor hyperviscosity takes into account basically both horizontal dimensions of that weird element, and applies it differently to each of those directions. And so it's a nice hyperviscosity operator. Henley?
Yes, I have a question on the ramp up. When we do higher resolution run from a previous coarser resolution run, always we need some ramp up time, damp out those adjustments waves. So I guess you need to do the same thing when you create the initial condition and render refine. Great. Okay.
Yeah, I would say that can be the trickiest part of this entire process, is getting a good first guess initial condition file that you can run for a few time steps without blowing up. So a lot of this stuff is going to be changing in the future. We're coming up with ideas for inline state rebalancing for things like that, so that it can do a hydrostatic type adjustment to the initial conditions with this topography field that you now are also feeding into it. So in the future, that's going to be a lot easier, we think.
Okay, that's great. Oh, and a quick question, another one. How do you visualize this? I mean, the refined grid, or with after you created the initial condition, you want to see if everything's okay.
There's there's NCL scripts that will generate that. There's also in the directories there, there's options there for, you can create a plugin for Visit, and you can use that program to display your grids and your data on there. But generally, the easiest thing to do is to run those NCL scripts and generate them that way.
Oh, so that's not just for the grid, but also for the data.
No, that's just for the grid, but for the data, yeah, there's a plugin for Visit, which is a graphing program, so you can display it that way. Okay. And then there's other options that I think people are coming up with Python things for graphing things. Generally, the difficulty is that that connectivity information is not in the history file, so you have to get it and put it in separately. That information that's in the lat.lon file that shows you how to connect the neighboring grid points.
Okay, thanks.
I'll second that. I have an unpopular hot take that NCL is the best plotting software out there for unstructured grids. But there are scripts that we have at NCAR here internally where you can use Python and plot an unstructured grid. But it uses sort of triangular elements it ends up sort of with a grid that's actually not true to what the actual grid is. And so using NCL and feeding in the script file with the connectivity, for me, I found is the easiest way to visualize what's going on in an unstructured grid.
Thanks.
Christian?
I have two questions. So I think you touch upon the time step. And is it correct to assume your time step setting must be the stable one for the smallest grid size? Yeah. It's not an adapted, so the time step is universal at all resolutions.
That's correct, yes.
And is that, so it's on the user to determine what the right time step is?
Yeah, that's part of the, once you get done creating your files, your grids, and you have to go through that iterative process to get a 5-day stable run going.
Yeah.
The settings that are there are, kind of good for any 120 to 240 kind of refinements. But once you go more than that, then, and even if those are there, you should go through and maybe play with them and iterate to make sure that you're not using up too much time. I mean, I went through and I was running a any 240 grid, and I had the same setting for any 120, and it worked for any 240. So the any 120 settings could have been I could have spent less computer time doing the any 120 runs, just in my hierarchy. So it's just, if you you should try and tailor them no matter what to your grid. So go through that iterative process and find out what is best for your grid, so you're find that optimal, that sweet spot, of optimal usage. Yeah.
And SE also has this interpolation option for the output. Of course, this is probably not the right way here for the variable resolution grid. The interpolate, it's a nameless option. Is that still usable, or would you just say you need to just do the output on a variable resolution mesh on the cube?
It depends what you're going to do with it. If you're just like, kind of like, I just want to see the big picture kind of thing, you can do the interpolated output. But the thing with that is you can always, once you've done it that way, then that data is already on that grid, and you've lost any. If you did it on the lower resolution, then you've lost all that information. But if you save it on its native grid, you can always interpolate afterwards and then graph it that way. And that way you can kind of preserve, if you want to go back and say, oh, I really want to look at the highest resolution region all by itself and look in detail, then you have that option. But if you just do the interpolated output, then you kind of give up that. But it depends on what your usage is and what you're looking for.
So I just want to check, it's not broken. Yeah, the interpolated output is an option.
I don't think
it works fine, and it ends up selecting if you don't specify the size of that grid, it'll end up selecting something close to the finest resolution lat long grid, so it'll be a bigger file than the raw output as well. So that's something you got to be careful about. And if I could follow up on the time stepping, Pat's install scripts will provide a user on LCAM with all these splits set to stuff, and just the point is that this is not gospel, and you are going to have to adjust it based on your grid. And I hate to shamelessly plug, but I have developed a document that I don't know if you've seen it, Christian, that exists in the repo under docs, and it's time steps for initial conditions for new grids.
Oh, okay, I didn't see it. Good, thank you for pointing it out.
Yeah, and there's a lot of really good information in here, if I do say so myself. But there's a lot of anecdotal examples on how you would stabilize a grid. And taking these CFL calculations that are ATM log, you don't necessarily need to follow them exactly. So you can get away with a time step that the log file is telling you might be unstable still. So that's all I wanted to highlight.
Yeah, thanks.
Tomas?
Yeah, hi guys, thanks for the tutorial. So I was just wondering, when you have all the grid files ready, can you apply them to any version of CESM which uses the spectral element core?
No.
Yes and no.
CSM 2.2 or later
Yeah.
is the earliest version you could use.
Yeah, but
Okay.
but not for like CSLAM. So if they have a CSLAM, it won't work for if you're trying to use a CSLAM option. Those grids are completely different. But yeah, and that's the one thing that's new is, we've been in this stable era, the MCT area, where it's been stable, and so everything has worked fairly easily. There were only cases there were problems is the location of the input files was moved in CSEG, and so all the paths were looking in the wrong place. But once you have it created, it should work from tag to tag fairly well. But you might have some minor things that come up along the way that you'll have to, that'll be part of the support and maintenance that the users have to be responsible for in dealing with. But there's been nothing really significant up until this transition to new OPSI. I think the only other thing was like one of the internally GLAND, was used as a tag for the Greenland case, and they changed it to GRIS. And so all the config files were incompatible once that happened. So that was like in some of the more recent tags, there would be a problem there. But, in general, you should be able to use it fairly consistency from one tag to another.
Okay, thanks. Yeah.
Can I just reiterate, this brought up an important point. I think CSLAM is not supported then under this new grid, under the variable resolution.
Yeah, I think Peter working on it, but yeah, there's no variable resolution for that option.
Okay, that's a good point. Mhm.
We might, I'm wondering if it might not be tenable to get CSLAM working for variable resolution, but if it's not, we still might be able to utilize the physics grid options that we have in CSM, where we can maybe run a PG, we can maybe run the physics on a finite volume PG2 type grid, like E3SM does.
Have you tested that? Is this?
No, I've just been thinking over the last couple of weeks that seems like something we could probably do without having to reinvent an advection scheme and just use CAMSE's advection scheme. So a little bit of speculation, but
Okay.
anyone else? Last burning desires before we end the meeting?
Yeah, last chance.
Will the slides become available on the? Yeah, I bet.
Yeah, they will, and it'll
bit.
all be also in the repository. So you download the tools. There'll be the docs directory. We'll have this PDF or this PowerPoint and all the notes for the step-by-step and all the related files that were used for that step-by-step testing. Yeah. And I guess one last thing is, if there's any questions, there's the bulletin board, high-res variable resolution section in the bulletin board, and that would be the best place to direct any questions that people have. So that way, once they're answered, then other people have similar questions. We can they can just see the bulletin board and say, "Oh, that's the answer there." We don't have to answer the same question over and over. Okay, so I guess with that, we'll call it quits, huh?
Thank you.
Yeah, thanks so much.